We use inequalities for graphing, as well as how to do some simple linear programming analysis using inequalities. So first, let's talk about what an inequality is. So remember our line, ax plus by equals c, is the standard equation for a line. Well, to make it an inequality, I keep the same format, ax plus by, but now I can choose one of the four inequalities. Right? I can choose, greater than or equal to, less than or equal to, or less than. Any of those can be picked and replaced by the equal sign. Now when you're solving these, typically what I do is I just solve them with the understanding of the equal sign and just pay attention kind of to the inequality. So as a refresher, if I wanted to graph y equals 3/2 x plus 4. So right now I've taken my equation from standard form and I've turned it into y equals mx plus b, where 4 is our y-intercept, so there is that point there. And then our slope is 3/2, so this is rise over run, or x over y. So if I start from a known point, my y-intercept, I go up 3, 1, 2, 3, and then right 2, 1, 2, there's my next point. Or I could go down 3, 1, 2, 3, and left 2, 1, 2, because two negatives make a positive, and I'm still there. And then I can connect my dots. I obviously use the software to have a nice line, but when you're graphing it on paper, this will assist you in quickly graphing it, or you can also use software to create your lines. So there is a refresher on how we graph lines. Now to do it as an inequality, I just replace my equal sign, and in this case with a greater than or equal to. And what you do is you graph a line. And so if it's equal to, your line is solid. And since it is the exact same line, I have the same line. The question is, where is the spot that's supposed to be shaded? Because when it's equal to, it has to be on the line. When it's an inequality, it could be on the line if it's equal to, or above or below it, depending on what satisfies it. So the way I typically do this is I just pick a point, and I always pick the easiest point to work with. So this point, 0, 0. And I know if you're looking at the screen, you're like, well, that's outside the shaded region. What I'm trying to show here is how do I prove what is where to color, right? And so if I put in 0 for x, I'll get 3/2 times 0 plus 4. And remember, y has to be 0, so I put 0, and I put my inequality in there. Well, 3/2 times 0 is 0, and then 0 plus 4 is 4. So I get 0 is greater than or equal to 4, which is not true. So I know that's not the proper shaded region. And then you can pick another point up here. So say we do -5 and 5, this point right here. So then y is 5, and that has to be greater than or equal to 3/2. Now, let's be a little bit later here. Let's drop this down to, let's go here to 4, just so we can do the calculations a little better. So we can still do 5, 4. We'll do this point. The reason I'm picking 4 is because I have a fraction, and it'll cancel out, plus 4. So 3/2 times 4, well, I can divide first, so 4 divided by 2 is 2, times 3 is 6, so I get 5 is greater than or equal to 6 plus, oh, sorry, -4. So this becomes a -6. And I'm rolling to the left side. -4 plus 4, which gives me -6 plus 4 is -2. And 5 is greater than or equal to -2. So be careful when you're picking your points. Don't lose your signs. And this puts it in there, so that point does satisfy. And you can pick a bunch of other points, but I basically just go for 2. And that verifies which way to color, so I know I got to color all this to the left as it is shown here. And so another one, 3/2 x plus 4, but notice this is greater than. And so in this case, I have a dashed line because it is not equal, which means I cannot use points on the line, but I can use any points to the left or above, however you want to look at it. And the reason I know is because it's still the same inequality, so you can still do the same test method. Here, same line, greater than or equal to, but it's colored this way And because now, again, I can try 0, 0 into this equation, I get 0 is less than or equal to 3 halves times 0 plus 4, right? And then 3 halves times 0 is 0 plus 4 is 4, so I get 4 is greater than or equal to 0. So this is true, so I color that way. So a quick recap, you graph just like it was a line y equals mx plus b. And then you figure out which side to shade by trying points in the equation. And there's another one with the dashed line because it's not greater than or equal to. So that is the foundation of inequalities. And then when we go into solving systems of linear inequalities, we're basically doing like we did before when we solved systems of equations, but now instead of them being equal, I have inequalities. And some definitions from this section. Bounded means the solution can be enclosed within a circle, and unbounded means it cannot. So I'm going to show you an example of each. So here is my first equation. X plus 2y is less than or equal to 8. 3x minus 2y is greater than or equal to 0. Right? And so if I take this first equation and I solve for y, I get 2y is less than or equal to negative x plus 8. I just moved it to the other side. Divide everything by 2. And I get y is less than or equal to negative 1/2 x plus 4. So I know I'm going to cross at 4. And so mine cut off because it actually solved based on the inequality, but I'll put the line in so we can see it. So 4 is right there. And then I go down 1 over 2. So there's that point. And then down 1 over 2. Down 1 over 2, there's that point. And so here's my line. I'm going to try to do my best to draw a straight line with a mouse. So there's my actual line. And this one also goes forever in this direction. That's the first line. And when I graph the second one, again, I can solve for y. So I'll change the color so you can see it. I get negative 2y is greater than or equal to negative 3x plus 0. Now I got to divide everything by negative 2. Now remember your rules of inequalities. If you divide or multiply by a negative, your sign has to switch. So now I get y is less than or equal to. I switch the sign because I divided by a negative. And that gives me a positive 3 halves x, because 2 negatives are positive. And 0 divided by anything is still just 0. I will put them in just so you can see it, which means this line has to cross at 0, which it does. And then if I go up 3, 1, 2, 3, and over 2, there's my point. Up 3, 1, 2, 3, over 2, 1, 2, there's my point. And so if I extend this line just so you can see how it extends, it's that way and that way. Now, I know I have basically 1, 2, 3, 4 pieces that it could technically be as of right now. And so what you have to do is try a point in each one. Now notice because 0, 0 is on this line, then it's not really going to help me graph it because this line actually goes to the point 0. So I would have to actually pick some points. So I'm going to pick one. Let's see. I got 2 fractions again. So we'll go with 1, 2. We'll do the point 4, negative 4. And the reason again is because if I put our x value here, no, we won't write over it. Let's go back to black. We can do negative 4 is less than or equal to negative 1/2. And we're going to put in a positive 4 here. And we're going to add 4. So negative 1/2 times 4 is negative 2. And negative 2 plus 4 is a positive 2. So I get negative 4 is less than or equal to a positive 2, which is true. So it works in the first equation. I come down here and I put in a negative 4 is less than or equal to 3 halves x to a positive 4. Again, 4 divided by 2 is 2 times 3 is 6. So I get negative 4 is less than or equal to 6, which is also true, so that it would be the area I would shade. So you could try a point from all 4 to figure out which one you work on. This problem is unbounded because it keeps going. Even though my graph stops, I keep shading in this direction, and it goes forever. So therefore, I can't enclose it in a circle because it goes forever. So this one is unbounded. Our next example, I use 3 equations, and again, you graph them, which I've just shown before, so you can keep graphing them. This one has the solution. But it is bounded because I can draw a circle around it. So if you graph all 3 of those lines, and then you figure out what point works, it would do it. And then because it is bounded, I can find the corners. And so the corners are just these points. Oops. So we have this point, which is 1, 10, right here. Then I have this other point down here, which is 10, 1. And then lastly, this point, which is the point 5, 2. So if something is bounded, I can create its corners. And the corners is what's going to take us into 5.3. We want to solve our problems using this linear program geometric approach. So here I have the steps of doing it. You got your decision variables, you got some constraints, you have an objective function, which is what you were trying to solve either through a min or max. And you're going to write out your problem using your constraints in linear equations using inequalities. If things are non-negative, which means they can only be positive, we'll put them in as necessary. And so theorem 1 says if the optimal value of an objective function in a linear problem exists, then the value must occur at one or more of the corner points. So that's why corner points. If there is an optimal value, it will be at the corners of the feasible region. If the linear program is bounded, then both the min and max value of the function exist. If it is unbounded, depending on which way it goes, it may not. And if it has no feasible region, which means the lines don't cross or touch, then there is no solution. And so we're going to use those theorems and kind of this idea to kind of come up with. So the first step is to graph the feasible region. And then we're going to create a table to put our points in. And then based off our corner points, we'll find the optimal solution. And then we can verify it in terms of the original problem. So there'll be a couple problems that you'll do. You'll do a problem where you're giving the functions. So our objective function is z equals 2x plus 3y, right? Because you're actually going to solve for z. And so you don't graph that one. That is where you're going to put your corner point solutions in. Subjected to, this is where you graph. So we have our first line, 2x plus y is greater than or equal to 10. X plus 2y is greater than or equal to 8. And here is my non-negative constraints. X has to be greater than or equal to 0, which means it has to be positive. And y has to be greater than or equal to 0, which also means it must be positive. So when I graph this, then I get this unbounded solution, right? So it does go in forever. So because it is unbounded in this direction, I know it can't have a max because it goes forever. But what I can find is a min. And so I can come to these points here, this point, this point, and this point, and I put them in my table. So I got a point 0, 10, I got the point 4, 2, and I got the point 8, 0. And then I just put them in the equation. So 2 times 0 plus 3 times 10 equals 30. Same thing, 2 times 4 plus 2 times, 3 times 2. Look at my table quick, because I'm putting them into the equation. 2 times 4 is 8. 3 times 2 is 6. I add them together and I get a 14. And then finally I do the last problem, 2 times 8 plus 3 times 0, which gives me 16. So I put those values in the table, and now I can say no max, because it's unbounded. Its min is 14, because that is the smallest point I got off the corner solutions, when x equals 4 and y equals 2. All right, so our last problem that we're going to discuss is how to do a word problem. So here we have a financial firm. And so you can read through the problem. You work for a financial firm, and you have someone that wants to invest $75,000 into a CD or a money market. There we go, mutual fund. And so the current mutual fund has a percent of 6%, CD has 8%. And so we have some constraints. The investor must invest a minimum of $10,000 in the mutual fund. You recommend, as the person doing this, at least twice as much in the CD as invested in the mutual fund. And so what are your recommendations to maximize the investor's return in these two types of accounts? And so to do that, we create our function. So our objection function is 6% times the mutual fund, 8% times the CD. And again, the investor only has $75,000. So we take the mutual, how much he puts in the mutual fund plus how much the investor puts in the CD. It has to add up to $75,000. I have to have twice as much in the mutual fund. I have to have less than or equal to twice as much in the mutual fund as I do in the CD. So there's where that inequality comes from. I have to put $10,000 in the mutual fund at a minimum, and then I have to put something in to the CD. So if I graph all four of these lines, right, this is my coordinates, and this is where the feasible region comes from. And again, I look at the three corners, sorry, not four corners, and I create the table, and I put the values in, and solve those into the equation, and there are my values. And so you can see I get a max of 5,800 when we invest 10,000 in the mutual fund and 65,000 into a CD. So this is how this type of problems can be solved. So through this week's lessons, you'll do linear inequalities, figure out which side to shade based on less than, greater than, or not equal to. Not equal to. Less than, greater than, less than, greater than, equal to, and not greater than, equal to. So we'll practice some shading, figure out your corner points, and this is a method. There's a lot of ways to do these. You can, like I said, use software to help you graph, or you can graph by paper. That's completely up to you. I have an Excel file in here where I use Solver. All Solver does is gives you the max, though it doesn't give you all the values. But there's a couple things. Feel free to message me if you have any questions. Thank you, and I'll talk to you soon.